To the surprise of no one, getting to space is expensive. Very, very expensive. Currently, it costs around $20,000 to send 1 kilogram into space. There has to be a better way. Introducing the space elevator. An unexpected solution that seems straight out of a science fiction story. Incidentally, it was popularized in the 1979 book The Fountains of Paradise by Arthur C. Clarke. To imagine a space elevator, think of an elevator without an elevator shaft, and it is tall. So tall, in fact, that at a minimum needs to extend into space nearly 6 times the radius of the Earth. Ideally, it would be nearly 16 times. Although such a height is nigh impossible to truly fathom, the actual design is very straightforward and ostensibly requires 4 parts. The anchor, to keep the entire structure attached to the Earth, the climber, a vehicle to shuttle cargo and passengers up and down the mind-bogglingly long cable, and the counterweight, which lies at the far end to provide the cable tension and upward centrifugal force, or centripetal if you want to be pedantic. This seems like it needs a lot of expensive materials and labor, and it does. Without a doubt, it would be the single most costly and difficult project undertaken by humankind, and make the construction of the ISS look like a little boy launching a cheap bottle rocket he bought from the discount hobby store. The upfront cost would be prodigious, but in the long run it will make sending objects and passengers into space exponentially cheaper, potentially taking that $20,000 per kilogram price tag and dropping it as low as $200 per kilogram. Now, with that tantalizing possibility, let's get to some physics.
One factor to take into consideration is the variation of gravity on the space elevator as you move further from the Earth's surface. So far, we have tended to approximate gravity as 9.8 meters per second squared. However, this only holds remotely true for objects close to the surface of the Earth. When trying to find the gravitational force on an object further from the Earth's surface, we must use the formula for gravity. Little g equals big G times m over r squared. In this equation, m is the Earth's mass, 5.98 times 10 to the 24th kilograms. R denotes the distance of the object from the center of Earth in meters, and G, big G, is the gravitational constant, 6.672 times 10 to the negative 11th Newton meters squared over kilograms squared. Based on this formula, if we assume that Earth's mass is remaining constant and the gravitational constant remains constant, as it probably should be, then the gravitational force on an object has an inverse relationship with the distance that the object is from the Earth's center. This pretty much abides by common sense, as we tend to think about astronauts floating freely about in space rather than undergoing gravitational force like on Earth's surface. Once again, in order to properly orbit, this space elevator needs to be above the geostationary, preferably at a height of 100,000 kilometers above the Earth's equator. Given that the radius of the Earth is about 6,371 kilometers, we find that the total radius of the space elevator's orbit around the Earth is 106,371 kilometers. So, plugging it into this equation, we have that the total radius of the space elevator's orbit around the Earth is about 106,371 kilometers, or 1.064 times 10 to the 8th meters. Also given is the Earth's mass, 5.98 times 10 to the 24th kilograms, and the gravitational constant, 6.672 times 10 to the negative 11th Newton meters squared over kilograms squared. For our equation, we obtain that the average force of gravity at this height is 0.035 newtons. When the space elevator is completed, its counterweight would experience a minuscule gravitational force of 0.035 newtons, or 0.35% of the gravity on Earth's surface. Note that this is for the counterweight alone and does not take into account the force of gravity on the cable and the climber, because that would require some physics calculations that are a bit too complicated for an intro to physics class.
Also, as we know, the Earth is constantly rotating, so if we were to build a space elevator, it would constantly be rotating as well, causing it to move in a uniform circular motion. This would be similar to spinning a ball on a string, which we have talked about in class on several occasions. As the Earth spins, the acceleration of the counterweight at the end of the tether would point down toward the center of the Earth. According to Newton's second law, the existence of centripetal acceleration and the mass of the counterweight indicate that there must be a force acting on the counterweight, also pointing toward the center of the Earth. This force would be the tension of the tether connecting the counterweight and the Earth. The magnitude of this force would be given by the equation absolute value of force is equal to mass times velocity squared all over radius. Given the speed at which the Earth is spinning at the equator, which is about 465.1 meters per second, and the radius of the Earth, which is about 6.371 times 10 to the 6th power meters, the angular velocity of the Earth can be found using the equation omega equals to velocity over radius, which would be about 7.3 times 10 to the negative 5 radians per second. Scientists expect that a space elevator would need to be around 36,000 kilometers long, but would hope to make one 100,000 kilometers long. So, assuming the length of the elevator to be 100,000 kilometers long, the radius from the center of the Earth to the counterweight would be 1.06371 times 10 to the 8 power meters. Because the elevator would be the same angular velocity, this equation, omega times radius is equal to velocity, can be used to find the speed at which the counterweight would travel, which would be about 7,800 meters per second. Given this information and assuming the counterweight had a weight of 5 times 10 to the 4th kilograms, the tension in the tether would be equal to almost 30,000 newtons. This is a very rough estimate because it neglects the weight of the elevator and assumes that the weight of the tether itself is negligible, but as you can see, there would be a lot of force on the tether. The material used to make the tether would have to be very strong in order to withstand the force, while also remaining extremely light. Currently, it is believed that carbon nanotubes, which are made up of carbon atoms arranged in hexagonal structures that connect to form a tube that has more empty space than mass, and can be much stronger than steel, one of the few materials that could potentially withstand this force. The problem with this, however, is that the longest carbon nanotube has only reached a length of around 30 centimeters. Just a bit too short to cover the needed 36,000 to 100,000 kilometers. The height from the equator to the counterweight, being 100,000 kilometers, and the force of gravity being 9.8 meters per second, during approximately the first half of the ascent, or the second half of the descent. This force then changes. Using the mass of the climber and the newtons of force we previously calculated that are on the counterweight at that high up, being 0.035 newtons, we can find that it would be about 5.7 times 10 to the negative 5 meters per second squared force of gravity at a point past 50,960 kilometers above the Earth's equator. To bring the climber to the counterweight in a timely manner of 2.5 days would require a speed of 400 kilometers per hour or 111.1 meters per second. However, you would need to accelerate to this speed very, very slowly in order to prevent any acceleration-related injuries to passengers. To calculate the energy necessary to bring the climber to the counterweight, as well as to calculate the power behind the ascent and calculate the necessary acceleration to bring the climber to the speed of 400 kilometers per hour, we would have to take into account this change in gravitational force once the approximate halfway height is reached.
While creating a space elevator would be extremely beneficial and is plausible in theory, and according to the cheesy animations included in this video, it is likely not going to happen anytime soon. Not only do we lack the engineering wizardry to create the aforementioned tether, but many have trepidations of the possibility of complications and the disastrous outcomes. For example, if the tether broke near the counterweight, and it would swing down and wrap around the Earth, destroying anything in its path, creating quite the spectacle for any astronauts on the ISS. I mean, how many times have you seen the Earth get slapped with an indestructible 100,000-kilometer death whip? So, well, it would be, as the kids say, far out or groovy to have a space elevator. The danger it poses means scientists are likely not going to take the risk to try and make one, well, unless they get handed a ridiculously large research grant.